Day 33, Kinetic Energy. Kinetic energy is motional energy, energy in motion, and the formula for kinetic energy is 1/2 mv squared. M is the mass of the particle and v is how fast it's going, its speed. So let's look at some proportions. Kinetic energy is equal to 1/2 mv squared. So if the kinetic energy is to remain constant, if the mass increases, the speed must decrease. These are inverse relationships or inverse proportions. So let's write that again. Kinetic energy is equal to 1/2 mv squared. And this time, I would like to leave the kinetic energy constant again, but the mass will decrease. If the mass decreases, the speed must increase. These relationships are known as inverse relationships, and they should make sense to you. Let's look at direct relationships. Let me write this out. Kinetic energy is 1/2 mv squared, and kinetic energy is equal to 1/2 mv squared. So in a direct relationship, let's hold the mass constant. If the kinetic energy increases, the speed will increase. This is a direct relationship. If the kinetic energy decreases, the speed will decrease if the mass is held constant. If we hold the speed constant, then if the mass increases, the kinetic energy will also increase. And if the mass decreases, the kinetic energy will decrease. So how is the kinetic energy affected if the speed changes? Let's say the initial kinetic energy initial, is proportional to the initial speed squared. So it's some factor of the initial speed. What happens when we double the speed? If you have twice the speed, that twice the speed is squared. So what happens to this new kinetic energy? Well, this new kinetic energy is going to be proportional to 4 times the initial speed squared. And so this new kinetic energy being proportional to 4 times the initial speed squared is proportional to the initial kinetic energy. That means that the kinetic energy final must be proportional to 4 times the initial kinetic energy. 4 times the initial energy. So doubling the speed does not double the kinetic energy. It increases the kinetic energy by a factor of 4. And if you triple the speed, the kinetic energy is going to increase by a factor of 9. So let's think about this for a minute. If you're on your bicycle traveling at 10 miles an hour and you fall off, it's going to hurt. I mean, there's a certain amount of energy that you have. So friction is going to bring your energy to 0 because you're going to stop, because your speed is going to go to 0. What if you were going 20 miles an hour on your bicycle? You're going twice as fast. That means you're going to have 4 times the energy. That means there's 4 times the energy to stop. What if you're going 30 miles an hour on your bicycle? If you're going 30 miles an hour, then that's 3 times the speed or 9 times the energy. What if you're going downhill and you're going 60 miles an hour on your bicycle? 60 miles an hour. What is your kinetic energy compared to the kinetic energy that you would have at 10 miles an hour? At 60 miles an hour, you're going 6 times as fast as you were at 10 miles an hour. That 6 is squared, so you'll have 36 times the energy. That means whatever energy it took to stop you at 10 miles an hour, when you're traveling at 60 miles an hour, it takes 36 times the frictional energy to get you to stop. Now think about a car. Think about the type of energy it takes to stop a car at 30 miles an hour. And then think about the type of energy it takes to stop a car that's traveling down the interstate at 90 miles an hour. 3 times as fast, 9 times the energy. Well, let's do a math calculation. It says determine the kinetic energy of a 0.145 kilogram baseball traveling at 40 meters per second. So we start off by writing the formula. Always, always, always start in by writing the formula. So you write the formula down, you plug in what you know, put in 0.145 kilograms for the mass, include your units, and you have the 40 meters per second is the speed, and that's squared. So now you get out your calculator and you'll find that the kinetic energy is 116 joules. So what I want you to do is to make sure that you write out the formula, you plug in what you know, you solve. Those are your strategies, your methods for success. That's what you need to do. Let me write this out again. Kinetic energy is equal to 1/2 mv squared. Now, in the sample problem we did, I gave you the mass and the speed, so you just plug it in. I could give you the kinetic energy and the speed and have you solve for the mass. So you may have to do a little bit of algebra in order to arrive at the correct solution. Let me give you an example. Let's say the kinetic energy is 10 joules, and we have 1/2 m, and I told you that the speed was 2 meters per second. 2 meters per second, and then that's squared. So we have our formula. Kinetic energy is 1/2 mv squared. We plug in what we know. I gave you the kinetic energy and I gave you the speed. Now we have to solve for this mass. The units of energy are joules. And so what is a joule? A joule is a newton times a meter. What is a newton? A newton is a kilogram meter per second squared times a meter. So we're going to get 10 kilograms meters squared per second squared. Those are the units for energy. And that is going to equal 1/2, and we have the mass, and this 2 is squared, so that's going to be 4, and these are meters squared per second squared. All right. We'll notice that we have meters squared per second squared, and those units will cancel because they're on both sides of the equation. 4 divided by 2 is 2, and so we'll have 2m is equal to 10 kilograms. That means that the mass is equal to, if we divide both sides by 2, the mass then would equal 5 kilograms. And that would be our solution. So sometimes you're going to have to do a little bit of algebra manipulation, but when you use the formula for kinetic energy, you have to know at least 2 of the 3 variables. Temperature is proportional to the average kinetic energy of the particles. That means if the temperature increases, the kinetic energy will do what? Increase. It's proportional to, it's directly proportional to, that's what that means. So if the temperature goes down, the kinetic energy goes down. So let's write that out. Temperature is proportional to the kinetic energy, and it says it's the average kinetic energy. That means we're not looking at a specific particle, we're looking at an average of particles. That's a big statement there because you have to make sure that you understand the meaning of the word average. I'm going to write something out. Kinetic energy is equal to 1/2 mv squared. So if we have a high temperature, we have a high kinetic energy. If we have a high kinetic energy, that means for particles of constant mass, we have to have a high speed. So that's just telling us that hot things move faster. The particles in a hot object are moving much faster than the particles in a cooler object. So if we say the reverse, if you have a low temperature, you must have a low kinetic energy, and if you have a low kinetic energy, then you're going to have a low speed. That's all it's saying. Let me write this out again. Temperature is proportional to the average kinetic energy, and kinetic energy is equal to 1/2 mv squared. Now, high temperature, high kinetic energy. High kinetic energy, high speed. Low temperature, low kinetic energy. Low kinetic energy, low speed. What happens when the particles are moving so slow they stop. If the particles are moving so slow that they stop, that means the speed of the particles goes to zero. And that means the kinetic energy is zero. And if the kinetic energy is zero, since the temperature is proportional to that average kinetic energy, if that's zero, we get something interesting. Absolute zero. That's what we call it. This is the coldest you can get. Absolute zero. At absolute zero, all thermal motion ceases. This is the coldest possible temperature. So what does it mean to be twice as warm? It means if you have something that is at 10 Kelvin, to be twice as warm, the temperature would have to reach 20 Kelvin. So if we were wanting to determine something that has twice as much kinetic energy, we have to make sure that we use the appropriate temperature scale, and that scale is the Kelvin. Particles that are moving around with an average kinetic energy that have a temperature of about 50 Kelvin, well, those particles, they're moving around with a certain speed. They have a certain kinetic energy. They have a certain temperature. So if we want to double their speed, then we've doubled their kinetic energy, meaning we've doubled their temperature. So we're going to be looking for particles that are at 100 Kelvin. So if you're going to double the thermal energy in an object, you want to use the Kelvin scale. You do not want to use the Celsius or Fahrenheit scale. They will not give you the correct results. Like if you said 0 degrees Celsius or 0 degrees Kelvin, you know, what's twice that temperature? You might think, well, 0 degrees, 2 times 0 is still 0, so I'm not sure what twice that temperature would mean. So use the temperature in Kelvin. 4.184 joules equal 1 calorie. That's a conversion. Joules is a unit of energy. Calorie is a unit of energy. If I get a bag of M&Ms, or if I look on the product label of a food item, you'll notice that that food item is so many calories. Well, what happens is those calories are called food calories, and those are actually a capital C. That's capital C, that food calorie. And 1 food calorie is equivalent to 1 kilocalorie. In other words, 1,000 of these small calories is equivalent to 1 food calorie. So 1 food calorie then would be equivalent to 4,184 joules. It turns out that a Hostess Twinkie is about 150 food calories. 150 food calories. How many joules is a Hostess Twinkie? Let's calculate it. All right, so we have our brackets. 1 food calorie is equivalent to 1,000 of the small calories. Okay, so now what do? 1 small calorie is equivalent to 4.184 joules. Set it up in the brackets. The food calories drop out, the little calories drop out, and I'm left with units of joules. So we just need to calculate it out. That's 150 times 1,000. Multiply that by 4.184. And I get 627,600 joules. Okay? So those are conversion factors you might find useful. So now it's time to do some problem solving. Work on the homework, and if you have questions, let me know. It's time to get to work.